Number 8, the quadratic function is using the description of the transformation from the parent function. A, write the function. B, graph the function and state its domain and range. Okay, so now what we're doing is we are going to graph this guy the way the transformation says. Quadratic function is reflected in the x-axis. Okay, so he's going downwards. Vertically stretched by a factor of 3. Okay, so vertically stretched by a factor vertically, so that's that. And he's translated to the left 4, and he's up 6. So that is, don't forget the quadratic. Then we got the domain, then it's quadratic, so that's all real numbers, so we could just domain. But in order to get the range, though, let's graph this guy. We know he's going down. He's going to go over 4. He's going to go up 6. So 1, 2, 3, 4, 5, 6. And then that's actually enough for us to get the range. But let's go ahead and just finish graphing this. We do know that the parent function is supposed to go over 1, down 1 if it's a reflection. But we're going to go over 1 and then down 3. Over 1, down 3. If we go over 2, we should go down 4, but we have to triple that. So now we're going to go down 12. So we're going to go over 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we'll mirror this guy over here. So this is a perfect graph right here with your 5 points. And now we can clearly see that our range is going from negative infinity down all the way up to that point, which is positive 6. We will actually include him. Okay. Now here we got the square root function is vertically. Good. I always like vertical. Horizontal is a pain in the neck. The square root function is vertically stretched by a factor of 5. Okay, so let's go ahead and go f of x equals. We got, and then it's horizontally stretched by a factor of 2. That's not fair. Then translated left 2, down 8. Okay, so left 2, down 8. So we got this guy. Then we've got a horizontal stretch by a factor of 2, so we have to do that. Then we translate 2 to the left. Okay, so notice that the horizontal is on the inside, vertical is on the outside. And then we're going to go down 8. Okay, so what does this guy look like? Well, we're going to go over 2 and then down 8. 1, 2, 3, 4, 5, 6, 7, 8. He's all the way at the very bottom. Okay. Now here's where it gets a little tricky because we both have a vertical stretch by a factor of 5. And then we're going to have a horizontal stretch by a factor of 2. So, what we're going to do then is we're going to look at, first of all, this is our new 0, 0. So, our new origin. So what we've got to do is let's go ahead and move over 1. Now, normally he should have went 1 and then 1. But he's got to go 1 and then 5. 1, 2, 3, 4, 5. Now I'm going to put a dot there, okay? Because, in fact, let me make it in red. Now my answer, nope, let's make it a different color. Make it in blue. So what should have happened is that he should have went over 1 and then up 1. But now he's got to go 1, 1, 2, 3, 4, 5. He's right there, okay? But because of the horizontal stretch, we actually have to, that 1, now we're going to double that distance, okay? We're going to double that distance so that it actually stretches by a factor of 2. And so now that 5 that we went over 1 up 5, we're going to go over 2 up 5. And that would account for the stretch. Now, is that enough for us to do? Maybe. Let's do the number. Let's do 4, right? So 1, 2, 3, 4. We're supposed to go over 4 up 2 at the parent function. But now we got to go over 8, and then we got to double the 5. We got to go 10. So now we got to double this guy, and we got to double that 5. So 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's all we got. That's good enough. That takes us pretty much through the graph. And again, what's happening is try to ignore this 1/2 because it makes you feel like you're supposed to shrink, okay? But not with a horizontal. Horizontal, you got a fraction in here, you're stretched by a factor of 2. So what used to go across by 1 is now doubling those, okay? It's you're stretching out how far you go to the left and right, or right. And then the vertical stretch will basically triple or quadruple or quintuple whatever you're doing, okay? Going up or down. So, anyways, we do have now a domain that we can clearly see that we are over at -2. We will include it, and we're going to go all the way to infinity, okay? And then our range actually is going to go all the way down from -8, I believe, right? 8, yep, -8, and we're going to go all the way to positive infinity, okay? Okay, so good problem. Those are kind of fun now that you understand. They're not fun when you don't understand. Now, by the way, definitely know you are allowed a graphing calculator. So if you do get into a pinch here, and you're like, whoa, 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 I'm losing sight here of this, okay, go ahead and type it into the calculator and get at least an estimate, and then you can hopefully piece it together, okay? All right, so we'll finish this page for this video. Use the graph to determine if the racial relations are symmetric or if they, to the x-axis, y-axis, are or the origin. Now, what we definitely don't want to do is we do not want to confirm this algebraically, okay? We're not going to do that. We will do this even odd algebraically, but we're not going to do symmetry, okay? So anyways, is this guy symmetrical? Okay, looks like he could fold on the x-axis, so he is symmetric to the x-axis. Now, believe it or not, this is actually really important for Calculus 2, okay? This is preparing you for basically cutting your work in half if you can see symmetry. So this guy is symmetric on the y-axis, and it's actually kind of hard to explain other than you seeing it. You can just see how it folds here, okay? This guy is symmetric if we were to put a pin right here and rotate it 180 degrees, he will look the same. So he is symmetric to the origin, okay? So just no, I mean, it's pretty obvious these guys, the symmetry here. Just remember that this guy is symmetric to the origin. Put a pin right here. Turn your paper 180 degrees. If he looks the same, then he is symmetric to the origin. All of these symmetries are very, very important for moving into calculus, especially Calc 2. Okay, so what about this? Okay, now what we're testing here is if we are testing if this guy equals this. Okay, if that is the case, he is odd. Or if this is the case, if nothing changes, then he is even. So if you exchange the x, then you get a negative version of the entire function, then he is odd. If you exchange the x and give him a negative sign and you get the same output, then he is even. Okay. If neither of these two happen, it is neither. So let's see what happens. You can actually see here if I did this. Now you do technically you must actually show me that you know what you're doing here, okay? So go ahead and just make this little step. This is really just a technicality. This is literally a proof, okay? So if you notice though that nothing changes, okay, because if you square a negative, he's the same, then you're just making a statement that, by the way, he equals the same. That is the original function. So f of x. So this right here is evidence that you just proved this guy. Okay? So therefore, even. Therefore, f of x, let's put f of x as even. That's even better. Okay? All right, this one. Let's go ahead and then exchange this. Okay, Now what this is saying is that and you can actually take the cube root of -1. Okay, and we just showed that that actually equals the negative version of the original function. Okay, therefore, f of x is odd. Okay, beautiful, perfect.